Hey everyone, welcome to This Explainer. I am so excited to have you here today. For the next few minutes, I actually want you to completely change how you see yourself. You're not just a viewer right now. You, my friend, are a biological detective. Today, we're opening up the Biologist Toolkit to learn one of the absolute most vital scientific skills out there, how to actively identify, categorize, and really make sense of the living world around us.
Okay, let's dive right into this. Imagine you're hiking through a dense forest, or maybe you're exploring a tide pool, and you spot a creature. It's totally alien to you. You've literally never seen it before in your life. How do you figure out what it is? Well, you can't just guess, and randomly flipping through an encyclopedia could take you years. You need a reliable, foolproof system.
Now, what's genuinely overwhelming is just how chaotic nature can actually be. I mean, look at the massive variety of these insect specimens on the screen. We share this planet with millions of different species. Some have spots, some have stripes, some have hard shells, and some are just completely bizarre. Without a structured system to categorize them, biology would be pure chaos. We desperately need a way to filter this wild diversity into something logical.
So, to turn all that chaos into order, here is our game plan for today. 1. The chaos of nature. 2. Step 1. Branching keys. 3. Step 2. Statement keys. 4. Step 3. Constructing keys. And 5. Why classification matters. All right, part 1. The chaos of nature and making sense of the wild.
As scientists looked at the chaotic wild we just saw, they realized centuries ago that they desperately needed an instruction manual to turn a messy, highly diverse ecosystem into a neat, organized filing cabinet. And they invented something absolutely brilliant. They invented the dichotomous key. This is the ultimate tool for our biological detective work. A dichotomous key is simply a set of questions about an organism that branch into two, leading you directly to its identity. The secret sauce here is the rule of two. The word dichotomous literally means branching into two. Every single time you face a choice in the system, there are only ever two options: yes or no, this way or that way. It completely removes all the guesswork.
Moving on to part 2. Step 1. Branching keys and how to visualize the path.
Let's look at how to actually read these biological maps visually. Here are the literal mechanics of using a branching key. It boils down to 4 incredibly simple, actionable steps. 1. Choose just one organism you want to identify. 2. Start at the very top of the key. 3. Look at the first question and answer yes or no based on what you see right there on the creature. 4. Follow the line down to the next question. You just keep repeating this process until you hit the creature's name.
Okay, let's actually do this together right now. Pick one creature in the diagram. Let's go with that flying insect on the bottom right. Start at the top box. Does it have legs? Well, looking at it, yes, it for sure does. So we follow the yes line down to the left. The next question asks, does it have more than 6 legs? No, it has exactly 6. So we follow the no line. Next question, does it have 4 wings? Looking really closely at our bug, no, it only has 2 visible wings. We follow the no line, and boom, we land right on housefly. We just successfully used a dichotomous key. If we had picked the worm instead, we would have answered no to legs, yes to rings, and found earthworm. It is a perfect logical funnel. Which brings us to part 3. Step 2. Statement keys and numbered logic. Now, please do not let this next part intimidate you. I promise, this is the exact same detective work using the exact same logic, it's just dressed up in a different outfit. Here is a side-by-side comparison to prove it. On the left, you've got our visual branch. Does it have legs, yes or no? On the right, you have the numbered statement style. Instead of boxes and arrows, it uses pairs of statements, like 1A and 1B. Statement 1A says, it has legs, go to 2. Statement 1B says, it does not have legs, go to 3. See? It's the exact same rule of 2. You read the pair, pick the one that is true for your creature, and it literally just tells you which number to jump to next. Let's test this logic out on a totally new key, this time classifying fish. Start at the top. Does it have stripes? If you answer no, you've immediately identified a horned shark. If yes, you move down. Are the stripes vertical? If no, it's a zebrafish. If yes, you go down again. Do the fins have spines? Yes means dragonfish, no means clownfish. See how fast that is? Every single question dramatically narrows the field of possibilities. And this brilliantly illustrates why those specific questions were chosen in the first place. Check out the horned shark on the left. If you ask, does it have stripes? The visual evidence is a clear, undeniable no. It has spots, so the key immediately identifies it. Now look at the clownfish on the right. Does it have stripes? Yes. Are they vertical? Yes, it perfectly validates our key. The whole system relies entirely on visible, physical traits that literally anyone can observe.
All right, part 4. Step 3. Constructing keys. Building your own tool.
Okay, we know how to read them. Now it's time to flip the script and empower you to build one. Look at these 4 wildcats. You've got the fluffy Pallas's cat, the leopard, the lynx with those distinctly pointed ears, and the tiger. If you had to build a key for these 4, what is the very first dividing line you would draw? Like, what distinct traits do you immediately see? You might notice the leopard has spots while the tiger has stripes. That is a perfect dichotomous branch. Does the cat have spots? Yes leads you to the leopard, no leads to the others, and then you just ask your next question. You are actively grouping them based on physical evidence. But wait, hold on a second. As you design your key, you have to be incredibly careful. Not all questions are created equal. Let me ask you this. What makes a physical trait useful? And which questions would actually ruin your key? Think about it for a second. If a key relies heavily on the rule of 2, what breaks that rule? So the absolutely crucial point here is that your questions must be entirely objective, not subjective at all. Take a look at this lineup of plants. If you wrote a key and your first question was, is the plant tall? That is a terrible question. I mean, tall compared to what? What I think is tall, you might think is short. It's totally subjective. But if you ask, does the plant have spines instead of leaves? Or does the flower have 5 or more petals? Those are fantastic questions. You can physically count the petals, you can clearly see the sharp spines on the cacti versus the broad green leaves on the flowering plant. Good keys always rely on undeniable facts.
Finally, part 5. Why classification matters and the real-world stakes.
Now you might be sitting there wondering, why go through all this effort? Well, check out this scenario. Stuff like this happens all over the world. A group of coffee traders wants to clear a piece of forest to build a coffee packing factory, which would create a lot of jobs and money. But there are birds living in that forest. One group of biologists uses their keys and claim there are 200 distinct, unique species of birds there, meaning the habitat is incredibly rare and legally has to be protected. Another group of biologists looks at those exact same birds and says, no, wait, according to these physical traits, half of these are actually the exact same species, just with slight variations. The forest isn't that rare. The entire fate of a rainforest, the survival of animal species, and the economic future of a town all hinge on getting that dichotomous key right. Correctly classifying species is literally how we make massive societal decisions. The power to observe, divide, and identify is literally the power to understand and protect our planet. So I'll leave you with this thought. If identifying a single trait, like the shape of a wing or the stripe on a fish, can help save an entire forest or discover a brand new species, what details will you look closer at today? Next time you step outside, don't just see a chaotic wall of green. See the branches, see the traits, and look at the natural world with the keen, structured eye of a biologist. Thanks for exploring with me today on this explainer, and keep your eyes open.